Hello, everyone. Hope you had a good weekend. Let's get started. We're going to start a new unit today. This unit is on feature selection, which we started talking about at the end of the last unit. And we'll also learn a few other important concepts. So our demo is based on this data set that has to do with PSA. PSA is something that you can measure in the blood, and it's an indicator of prostate cancer. It's the most common tool that doctors use for screening. And so there's this data set, this data set comes from a study where they measured the PSA level of 97 men prior to getting their prostates removed, and they measured all these different biometrics at the same time. And then this gives us a data set where we can try to predict the PSA from the biometrics. So again, there's 97 patients. There are, in this case, 8 features, which is not very many, so we can play with all kinds of different feature selection techniques. So the target variable is the log PSA, and then there's all these other variables in the data set: log of the cancer volume, log of the prostate weight, the age of the patient, and so on. This data set is in this book, The Elements of Statistical Learning, which is probably the most famous statistician's textbook for machine learning stuff. So it's a pretty well-known data set. So, all right, let's see what happens if we play with this data. So first we're going to try what we've learned so far, which is multiple linear regression. So in this case, what's the equation? So this gives me a chance to, is Alex Miller here? Yeah, so what would the equation here be for y hat in terms of the betas and the x's?
Beta naught plus beta 1 and xi 1.
Okay, yeah, we'll leave the i's off for now, but.
The beta d xd.
Right, okay. So that's what we've seen. In this case, we have d equals 8 features. And so, again, in this case, we might ask, why are we doing linear regression? And the answer we gave before is because it's easy. We can derive the equations in closed form. They're pretty simple to implement. It's an instance of least squares fitting. But there's actually another really important reason that occurs if you're doing like science or medicine or something, and you collected this data set and you want to interpret it. You want to know, like in this case, which of those different biometrics are most important to PSA. And one way you can do that is you can do this fitting that we've described. You can then look at the values of beta 1 through beta d, and if you see that one of these values is much higher than the others, that suggests that particular feature is much more important to predicting the targets than the other ones, and okay, that's really important. So this is the other advantage of linear methods. If you had, and here we're talking about linear in the data. So for example, if I had a polynomial model and I have all these different powers of these x's, then or some crazy nonlinear combinations of the x's, then it's less clear what it means when that coefficient has to be large. Here it's very clear if this one particular beta is large, it's because this x is important. Okay. Now there is one catch that you have to be careful if you look at the betas and you look at their sizes, you have to make sure that the sizes of the x's have also been somewhat normalized. Because, for example, in a practical data set, these x's have totally different meanings. They could have totally different units. the sizes of the x's could be vastly different. Some could be, millions, some could be tiny fractions of one. So for example, like if this guy was units millions and this one was units of ones, then you would expect to have an equal effect on y. This would have to be much, much smaller than this, right? Because it has to counteract the effect of the size of the x. So if you want to do this interpretation, you have to be careful, and you want to make sure that these x's are roughly the same size. And we can do that using a normalization process that I'll describe just in a few more slides. But so that's sort of a caveat. If some of you may have realized, as I was saying, we can just look at the betas, that's not entirely true unless the x's themselves are roughly the same size. And then if so, then yes, a larger beta means that feature has a larger effect on the target. And so that could be really useful to know. Okay. All right, any questions so far? Okay, so here we have a little snippet of code that's the standard thing we've seen. So our go-to method now for doing this linear fitting is to use the linear model.linear regression. For reasons that I will explain, we're going to force the intercept beta 0 to be 0. And that just will simplify our life, simplify some of the notation. And we can do that with the right normalization of the x's and the y's, as I'll show you. The other thing I want to call attention to is this other little code snippet down here, where we're using a command called cross-val score. So we're using k-fold cross-validation here to get a sense for how well this linear model is working. And the way that we described k-fold cross-validation before, at least the implementation, if you remember, there was like this double nested for loop, right? It was like a whole page of code to do this. Well, not surprisingly, there's shortcuts. So here's a one-line shortcut for that whole page of code, which is really useful to know about. This is this command cross-val score. Now, this is not the one that's doing, it's not trying to search over a parameter grid like of model orders like we saw before. This one, it's doing cross-validation of just a single model. So, you have this linear regression model, you have the data set, features, targets, and here you can tell it what kind of cross-validation you want to do. And you tell it how you want it to build its score. And so for us, we want to either minimize mean squared error or minimize RSS, or equivalently, we could be maximizing R squared. Those are all different options. Well, at least they're all sort of the same thing. Now, there is one other detail. When you specify scores in sklearn, the way that they're defined is higher scores should always be better, just across all the different scores it has implemented. And if you think about mean squared error, RSS, lower is better, right? So to make this work within the score framework, they negate it. And so now once you look at negative mean squared error, you want that to be as large as possible, as close to 0, right? So that's why the score is negative mean squared error, not just mean squared error, just because sklearn wants all of its scores to increase with goodness. Okay, so that's essentially it. It's really convenient. You just give it the model, you give it the data, you tell it what kind of cross-validation you want it to do, and then it does it for you. And what it will output here is a vector of the different, in this case, negative mean squared errors, one for each of the test folds, or k-folds. And so here we're just negating that negative mean squared error, and we're averaging over the test folds, and we're finding that there's a particular cross-validation MSE 0.404, which will be sort of like a reference point. This is just the plain vanilla least squares, so we can see if we can improve on this. So one other little thing here is that for the cross-validation argument, you can give it a number like 5, in which case it just does 5-fold cross-validation. However, when it does that, it does not do any shuffling, which can be a bit dangerous. So if you want to do shuffled cross-validation, you have to use the k-fold command that we saw before. to make a k-fold object, and then you can plug that object in here. What I did is, in this demo, I created what's called a recursive k-fold object. So what it does is it's doing, I think it's tenfold cross-validation, but it's doing it a bunch of different times with different random seeds to try to increase its accuracy. Because as we saw before, when you use one random seed, you get one shuffling, and it's just like one kind of estimate of the mean squared error. And if you do it a bunch of times and you average results, you can kind of remove the statistical error or reduce it. So that's what this RKF is. It's in the demo. Okay, so this is just our first attempt with regular old least squares linear regression. All right, any questions so far? Okay, so now let's come to the main topic of this unit, which is feature selection. And now that we learned about the bias variance trade-off, we learned one of the guiding principles of machine learning, which is that if you have too complicated of a model, or in this case, too many features, the results, your performance on test data is compromised by a large error variance. So that means that if you would imagine doing many experiments with different training sets, different test sets, what you would find is that you would have a high fluctuation in your test predictions. They would be very inconsistent. And when you average over all those experiments, you see that just increases your overall error. On the other hand, we saw that if you have too few features in your model or too simple of a model, then you get a large bias. Like your model just can't quite model what's really there in the data. It does something overly simplistic, and there's just sort of a persistent gap in terms of like your average predictions are not matching the average truth. So those are the sort of two different ways you can see the error in machine learning is high variance, overfitting, or high bias, underfitting. And so this is where we have this important trade-off. So in the last unit, we had sort of a simple idea where we somehow knew the ranking of our features. Because we were using a polynomial, our objective was to find the polynomial order, and so that means that we always keep the low polynomial, low order coefficients, and then we're just trying to figure out how high do we go. So we know which ones we want to remove. But now, when we step back and we do feature selection, it's a more complicated problem. We have a total of D features. We don't know, we have no ranking among them. We don't know which feature is better than any others. So we're really considering subsets of these D features. And in total, there are 2 to the D possible subsets with D total features, which is a lot when D is large. And so if D is small enough, you can do exhaustive search, which is the optimal method. And essentially for every possible subset, you run k-fold cross-validation, and you just look to see which is the best subset of features, and you use that. It's straightforward, but computationally, it takes a while if you have a lot of data and if D is large. And if D is, beyond, 15 or 20 or so, it's just impossible. It's computationally impractical to do that. So this is the main issue with that. So in this unit, we're going to spend time learning about some suboptimal techniques that are practical, and we're going to focus on sort of 3 varieties of them. One are some methods that are called stepwise or greedy methods. Another method is a feature ranking method or feature ranking methods. And the last are regularization-based methods, and they're all pretty different. We're going to spend most of our time on these regularization-based methods. Okay, so that's sort of a bird's eye view. Any questions before we move on? Okay, so, we just have one page on stepwise methods. So sometimes they're called stepwise selection or stepwise regression. And there's essentially 2 varieties, forward selection or backwards elimination. And so this is how forward selection goes. The first thing you do is you try each of your D features alone in isolation, and you figure out which is the best one. And you do that by training your model and then validating it on a different data set than it was trained. And so we've learned several ways to do that. The simplest way is you split your data into two non-overlapping folds, and you train on one, testing the other. But we saw that a more sophisticated way to do it is k-fold cross-validation, where you split your data into k-folds. You use k-1 for training, 1 for test, and then you keep swapping around which one you use for test. So you end up fitting the model k different times, averaging the results. But anyway, you're going to do this now for each single feature. And after this, you will figure out which is the best single feature to use. And then you'll add that to your list of features you're going to keep. Now you're going to go through the remaining D-1 features, and you're going to say which one of those is best to combine with the one I already decided to keep. So you're going to go through these D-1 possibilities of a pair of features. And you'll do train, cross-validate on each one, and you'll finally figure out, okay, this is the feature I'm going to combine with that first one I chose, and this is now going to be my two features I'm going to keep. And then you repeat this. You figure out the third feature, you figure out the fourth, and so on and so on. And you can go until there's no more features left, but usually you stop a little early, because what you see is, when you use one feature, you're not going to get great performance. When you use two features, performance starts to get better. Your RSS starts to go down. 3 features, maybe it goes down again and again and again. But at some point, you're using too many features and your RSS starts to climb. And so when you start to see it climb, okay, I've gone too far. Now I'm using too many features, and you just stop there. Okay, so that's the forward selection. First, figure out the single best feature, figure out the best one to add to it, the best one to add to that pair, and so on, using cross-validation at every stage. Okay, is that idea clear? Okay, so this method is not optimal in the sense that it's greedy, it's myopic, which means it's not really looking very far ahead. And just in general, like in life, as you know, it's good to think ahead and not just do what you want to do at the moment, because if you do what you want to do at the moment, in the long run, that might not be a good decision. So here, when you just select that one feature to add to your kept set, that might not be the best. It might be, in hindsight, that there's some other combination of features that's better than using that one. So it's impossible to see that if you just consider adding one at a time. That's greedy and it's suboptimal. Now, it might work pretty well. In practice, it actually does work relatively well, but you're not guaranteed to get the optimal result. So it's a very practical method, but it's not optimal. Okay, so that is the forward selection. Is that sort of clear, what we're doing there? Any questions on that? Okay, so then backwards elimination is very similar, but you start with all the features, you train that model, and then you consider removing the first, or removing the second, or removing the third, and you see, if I remove a single one, which is the best one to remove based on the cross-validation performance. And then once you figure out, okay, that's the one I'm going to remove, you remove it forever. Now you have D-1 features, and you figure out which is the single next feature that I should remove based on whichever minimizes your cross-validation, mean squared error, or whatever. And then you remove that, and so on. And you keep removing features. Your RSS should get better and better. At some point, you've removed too many features. Bias starts to take over. It's no longer that you're trying to reduce variance. Now, bias is the issue, and so you stop. If you start to see the RSS go up again, you say, okay, I've removed too many features. So in Spirit, it's similar. It just works from the back. Okay, so those are basically the two methods for stepwise selection. They're suboptimal because they're greedy, but they often work well. So it's a bit expensive. Still it's not like you have 2 to the power D, but you have at every stage you have on the order of D times K, where K is the number of cross-validation folds. So it is still a little bit expensive. Sometimes it's cheaper to start with an empty model. If you know you're only going to have a few features, it's better to start with an empty model and do forward selection. If you know you're going to have most of your features, it's probably best to start with the full model and just remove a few. Okay. You might get different results if you start from the full model or the empty and try to meet in the middle. They're not guaranteed to match. They might, but they might not. And these are implemented very nicely in sklearn in sequential feature selector. You just give it the model, you give it the data, you give it the cross-validation type you want to do, and it has a few other parameters, for the stopping criteria and so on. But otherwise, it's very easy to use. Just a few lines of code. Okay, so that's this method. Are there any questions on the stepwise methods? All right, making sense? Okay. All right, so there's another class of methods that I find doesn't work nearly as well, although they're still talked about a lot in the literature and books, so I think I should at least talk about them. And the idea is basically to somehow rank your features. So an example of how you might rank them is you might rank them in order of how correlated is each single feature with the target. This is based on the intuition that if you have high correlation between a feature and target, it must be really useful for predicting that target, right? But it's not that simple. If you were just looking at one feature at a time, yes, correlation, as we learned in Unit 1, is everything. But if you have multiple features and you can use them together, it's hard to see what the results will be from just looking at correlation one feature at a time. But in any case, the way this works is you somehow rank your features in correlation, let's say in decreasing correlation from most correlated to least correlated. And now you have a very clear ranking. And now you treat it as a model or a selection problem. You just say, do I use, the first P, or do I use all of them? Do I use one less? Do I use two less? And because it's a model or a selection problem, now you just have D different final models to evaluate. You can do that easily with cross-validation. So first step is ranking. Second step is model or selection with cross-validation. Okay, so there's a lot of ways that this can fall short. For example, maybe you have two features that are very similar to each other and very highly correlated with the target. So intuitively, if they're very correlated with each other, there's probably a lot of redundancy. Like, you shouldn't be using both if they're telling you almost the same thing. On the other hand, this method would not be able to pick up on the fact that you should throw out one of them because they're both highly correlated with the target. It would think of both of them as very important. So it's just an example where this falls short. And there definitely are more complicated versions where they somehow tried to penalize cross-correlations among the features while rewarding correlations with the target. And then correlation is not the only choice. There's all sorts of different statistics that you could use that try to tell you something about how good an individual feature is at predicting a target. And they're so-called univariate statistics because they just depend on a single feature. Not multivariate would be like looking at a whole bunch of features together. No, there's just one feature at a time compared to the target. If you don't want to use correlation, maybe you could use something else like mutual information that comes from information theory, or various other metrics, which I'm not going to get into the details. They're things that are implemented in scikit-learn. You could read about them if you like. Permutation importance is another interesting one where you have some model and you fit that model by randomly shuffling all the entries in one feature. So, for a particular feature, you have n different samples, right, across your data set. What you do is you just randomly shuffle those samples for that feature, which makes that feature essentially useless for prediction. However, that feature still has all the same univariate statistics as it did before you shuffled it. So it's sort of like saying, I'm going to put in a noise-like feature, but it's going to have all the same statistics as my original feature. It's just you've broken the link between that and the target by shuffling. So the idea is you could come up with a ranking that way. You could see how well your model performs if you shuffle the first feature. If it is a lot worse than using that first feature, that suggests that's an important feature, because when you shuffled it, it broke everything. On the other hand, if you have some other feature where you shuffle it and it doesn't really change things much, that's probably not a very useful feature. It's probably not that important. So that's the idea behind permutation importance. But permutation importance has the same issue with correlation as we talked about before. So there's various options here. A lot of them are implemented in this select k-best function. So you can just kind of choose them and try different ones. But what I find is that these don't work that well. They're very inexpensive because all you have to do is rank, and then you don't have to do all this cross-validation stuff. So very, very inexpensive to do, but it doesn't work all that well. All right, so this is the second class of methods. So this is all we'll say about them. Are there any questions on this class of methods? Okay. So then we'll spend most of our time working on this third class of methods, which are based on what are called regularization. And the idea behind regularization is that you take your original cost function, which for us has been RSS, but it could be some other cost, and then you add to it a term that somehow penalizes the use of a lot of features. And the intuition is that if a feature is not really that useful to prediction, you'll see the cost of that feature in the regularization term. The regularization will be like, you're using that, there's a cost to it. And then you won't see like a reward from it because it's not really reducing your original RSS. So because there's like a penalty to using it, but no real gain in using it, it will say, well, you probably shouldn't use it. On the other hand, if there's a really useful feature, yes, you get a penalty from using it, but you get a huge reward from using it. So overall, you win out. And it will say, okay, yes, use that one. So that's sort of the intuition behind regularization. And we're going to consider two different forms, ridge regression and lasso, which are both very, very famous and useful methods. Okay, so maybe let's dive into to some of these details. I think it will make a little bit more sense. So the way that we have been doing linear regression is we have been constructing a set of parameters using least squares. Mathematically, we can write it as follows. Beta is the arg min over beta vectors of the function RSS of beta. Okay, so if you remember, the meaning behind the arg says, okay, so if the arg wasn't there and you want to minimize RSS, the output of this thing would be the lowest value of the RSS. We're not interested in the lowest value of the RSS. We're interested in the beta that causes that lowest value. So that's what the arg says. It's find the minimizer, not the minimum, of RSS. So minimizer, that's what the argument says. Okay. And moreover, how can we write RSS as a function of beta? So let me ask, is Ram Saiganesh here? Yeah. So do you remember any expressions for?
Yeah. It would be y minus the summation of the squares from I equals 1 to n of y minus y hat. Or I guess beta times x
Okay, so let's say I have yi, and then what how do I write the next term?
It'd be the vector product of features and data, which would be x.
Okay, we got it, x transpose. And then we have to have a 1 here, right? And then we have, oh, sorry, this needs an I. And then we can sum this over our different samples. Okay, so this is our y hat I. All right, so that is one way we can write the RSS, where you can clearly see the effect of the beta and how RSS is defined. So that's where we're starting from. And the idea is to just keep this, but make a slight modification to it, which is to somehow penalize the use of these features. Meaning, if I set a feature, if I don't want to use one of my features, let's say I don't want to use x1, all I need to do is set beta 1 to 0, right? If beta 1 is 0, then in my linear model, x1 is ignored. So using a feature is equivalent to beta j, using the jth feature is equivalent to beta j being non-zero. Okay, and the idea, like I said before, don't use the jth feature unless using it really reduces your RSS. Otherwise, it's just not worth it. Don't use it at all. And then that's how we can do feature selection. Okay. Set beta j hat to 0 unless the RSS is significantly reduced by a non-zero value. Okay, so so the way that we can do this in terms of the math is we do arg min over the beta vector, and now we have this new term I'll call j beta, where j beta is the RSS as before, plus this new term phi of beta, which is the penalty. Okay, and this term encourages the beta hats to be 0. By saying there's going to be a penalty if you use a non-zero beta. It's going to cost you something. You will really need to make this much smaller to offset the costs I'm going to charge you for using that non-zero beta. And so that's sort of the idea. Is this kind of making sense? All right, any questions on anything so far? Okay, so the main question then is, how do we select this phi function? And it turns out there are tons and tons of different ways to select it, but we're going to focus on the two simplest and most popular ways. The first one is known as L2 regularization. So we're going to have some coefficient alpha, which we will have to choose. And we're going to have a summation over j, the feature index. We'll have beta j squared. So we're penalizing the sum squared coefficients, adjusted by some alpha that adjusts the overall strength of that penalty. That will be one option. The other option is very similar, but instead of the sum squared, we'll do the sum of the absolute values. And that is called L1 regularization. Okay, and to get some insight into the differences between them, we have this picture on the right. And so let's see, is Lakeith Narakurthi here? Yeah. What about William Sirpotowski?
Yeah, I'm here.
Okay, so intuitively, qualitatively, what would you say, which is the stronger penalty for small betas?
The red one, B.
Yeah.
Probably the absolute minimum.
Yeah, because as you deviate from the origin here, it complains. It starts to go up. Whereas the blue one, if you deviate a little from the origin, it doesn't really care very much. But what about large betas? The quadratic one. The blue one is saying, okay, you can deviate from 0 a little bit, but if you deviate a lot, I'm gonna get really mad. Whereas this other red one is saying, it's okay. I'm not going to freak out if you have a large value as much as this. So that's sort of the intuition that really changes how they behave. One of them allows small deviations, but really doesn't want large deviations, and the other cares about small deviations, but doesn't freak out with large deviations from 0. So, okay, so we'll see that reflected in how they behave when we start to see some experiments. Okay, so both of them, as you can see, they penalize non-zero beta. So if all your betas are 0, these regularization terms are exactly 0, right? They're totally happy. 0 is the smallest value that they can become, and they're 0 when you have all 0 weights. But of course, having all your beta 0 is silly because that means you're ignoring all your features. So that's probably not going to happen. You certainly don't want that to happen. And then also in common is there's this overall weight that sort of is there to adjust the strength of the regularization relative to your main loss function. And another important thing here is that if you look closely, regularization is not being applied to the intercept term beta 0. These sums are starting with 1, not 0. So that intercept term is just, you just want to let that be what it's going to be. That is sort of compensating for some change in your targets. If your overall target shift, then the intercept term shifts than your model. So that's just, however your targets are designed, that intercept is there to compensate. So we're not going to penalize beta 0, but we are going to penalize all these other betas. Okay, so these are the ones we'll focus on. Any questions on these? Yes.
So this is penalizing like large magnitudes, and if you have different features, like you were mentioning earlier, that were different scaled, like if you have one feature that maybe there's a big correlation, but it's got a small X range,
Yeah.
its beta would be really big.
Exactly.
Maybe it would, like,
Exactly. That's a great lead into the next slide. The point is, if you want to do this, you have to standardize your data, meaning you have to normalize all your X's to have roughly the same range, because essentially these penalties treat the beta values identically. They're saying all the betas are penalized equally. Beta 1 is no different than beta 2 or beta 3. And so that means that your features, like, it wouldn't work to have X1 be massive and X2 be tiny, because then the betas would have to kind of compensate for those X's, but then the regularization would effectively penalize one of those betas much more than the other because it's really big or really small. So, so that's the idea. We basically want to normalize the X's to get rid of that problem. And there's different ways to do this. One way you could think of doing it is to set the overall energy or sum of the squares for each of those X's to a constant. And as long as you're going to scale it, you may as well just choose whatever constant you want. Maybe you want that constant to be 1. So here, notice I'm doing this for each J, and I'm averaging over the samples in my data set I. We also know that this sum of squares is equal to the squared sample mean for the jth feature plus the variance of the jth feature. So another way you can think about this is, well, somehow I have to balance these two terms. So something convenient happens. If we remove the mean of our targets and each of our jth features, we get beta 0 equals 0. This comes from an equation we derived. So beta 0 is y bar minus x bar transpose beta 1 through d. I'm writing that from memory. I think it's true. So this is, again, the target mean. This is the vector of feature means, and then these are the least squares coefficients for indices 1 through d, the slope coefficients. And so from this equation, you can see that if I set my target mean to 0 and all my feature means to 0, then my least squares beta hat also goes to 0. And what's convenient about that is then I don't have to write it in any equations. I don't have to solve for it. I just know it's 0. So that's actually a common thing to do, is to set all those means, sample means, to 0. Conveniently, we get beta hat 0 equals 0. And so if we know that this is set to 0, then that means that we just need to set our variances to 1. And that kind of explains the typical method. So it goes like this. You take your xij, you subtract the sample mean for that feature j, and you divide by the sample standard deviation for that feature j. And so if you remove the sample mean, the new variable is 0 sample mean, right? So this is how we can get 0 sample mean. And then if you divide by the standard deviation, then this new thing has a standard deviation of 1, which is exactly what we want here. And so we just kind of we overwrite our features with these new scaled features, and then we just work with them. Okay, similarly for y, we can take yi, we subtract its sample mean, we divide by its sy, its standard deviation, and now the yi's are 0 mean and also normalized. The normalization of the y's is not really important. I'm just doing this for consistency. We can use the same procedure on both. What really matters more is that you remove the sample mean here. Okay, so that's what we call standardization. It's like normalization, but you're also removing the mean too. Okay, is that making sense in terms of a procedure definition? Okay, so how you do this is in scikit-learn, there's something called the standard scalar. And it is a function that can do this for you. So the first thing you do is you instantiate that function. The next thing you do is, so first we're going to standardize the features. So we just do that in one line. And essentially this function is doing two things. It's fitting some parameters to the data. Basically, it's computing those things. That's what it does in the fit step. And in the transform step, it applies those fitted parameters using that equation. There's also a function that's just fit alone, and then there's a transform alone where whatever's, of these that are stored, it applies them. But here we're just doing both together. So we're taking our original raw features and we're getting our new standardized features that we can use for training. Okay. Then we're doing the same thing to the data, except there's this one little annoyance that the way that this function is written, it only works on matrices, and the target data, I should say it works on two-dimensional quantities. The target data in scikit-learn, this is very different from MATLAB, but in scikit-learn, when you have a one-dimensional quantity, so in MATLAB, if you have like a vector, it could either be a column vector or a row vector. And essentially, it's a matrix with either one row or one column. But in scikit-learn, when you have a vector, there's only one dimension. It's not a two-dimensional thing, a matrix with one row or one column. So it just literally has a length, and that's it. And so this command wants the input to be a matrix. So the way you can trick it to think that this is actually a matrix is you say, okay, add another dimension that has a value of 1. And this -1 says, essentially just, whatever length this is, use that information. And this is what this is going to do is it's going to create a matrix, a 1-column matrix from this so that you can do this transformation. And then it's going to throw away that extra unneeded dimension to get back to a vector. So vector to matrix, back to vector. This is just NumPy stuff. Okay, so that is that's how we standardized. And yeah, one other comment is, and this is a very important comment. So we are doing this with the training data, right? If you standardize your training data and you don't standardize your test data is like shifted, scaled, the performance of your trained model will be terrible on the test data, right? Test data looks completely different than the training data. So your test data must also be standardized. It must also be shifted and scaled. But here's a point that's a little bit less obvious. The particular shift and scale that you use to standardize your test data must be exactly the same shift and scale that you use for your training data. In other words, these parameters here, the shift and the scale, were computed from the training data. Those are the same parameters you want to use on the test data too. You don't want to recompute these from the test data because if you do, turns out they're not the same and it won't work that well. And every semester when it comes to the final project, there's some subset of you guys who don't pay attention to what I'm saying here. And your models in the Kaggle competition are just a little bit worse. And it's because of this almost always. I mean, this is one of the ingredients. This little error where you use the test mean and the test standard deviation will just make your performance a little bit worse than everyone else's, and you'll just not be able to compete, even if you're doing everything else right. So this is a really important little thing here. You have to use the training statistics, not the test statistics. Another way to think about this, let's say I had a test data set that had one sample and one sample only. In that case, there's absolutely no way to even compute the test standard deviation from a single sample, right? I need at least 2. So you can't even compute these in all cases for the test data. Okay, but you don't want to. You want to use the training data. So you end up doing the scalar.fit transform, and then you plug in the test data, but you only use the transform version. You don't refit it. Okay, does that make sense, what I was just describing? Are there any questions on that? Okay, so I hope all you guys remember this and do it in your final projects. It will help you. Okay, great. So any questions on standardization? All right, so from now on, throughout the rest of the semester, this is going to be pretty much what you always do when you get a new data set. You load it, second step, you standardize it, and you just work with the standardized data from then on. Okay. All right, so we talked about the regularizations individually, and we talked about our RSS cost. And here you can see now we're explicitly adding them to get 2 versions of an overall cost, RSS plus regularization, that have particular names in the literature. I don't know where this first name comes from, ridge regression, but it's the one you get when you combine RSS with L2 regularization. The other name, it's short for least absolute scaling and shrinkage operator, I think, is when you combine RSS with L1 regularization. So those are the things we're going to focus on, and for now at least. And there is a way to write this without summations a little bit more cleanly. Let's see if, is Zacharias Tebben here? Yeah, so do you remember how we can write RSS without a sum? I'll give you a hint. It involves a norm. No? Okay. Okay, sure, no problem. So what we can do is we can stack all our y samples into a vector, bold y, and then we can, in this case, we can put all our training samples into this matrix X, our beta coefficients there, and this is the Euclidean norm. Sometimes people write a subscript 2 to denote Euclidean norm. We have not done that until now, but you'll see it sometimes. It's sort of optional. When the Euclidean norm is the usual norm, you don't need to write the 2 there. Everyone sort of knows. But sometimes, if you want to be extra careful to make sure people understand what you mean, you can put the 2 there. Okay, so that's how we can write this. Now, does anyone notice that I'm not using the A matrix? Why are we not using the A matrix but the X matrix? Exactly. So we're standardizing, so beta 0, 0. So we don't need that column of 1s in the A matrix. We just have the rest of the columns, which is our X matrix, just the feature data. Down this way we have our samples. Across this way we have our features. Okay, so that's what we have for RSS. And then for this second term, we have plus alpha. How can we write the next term with a norm? Is Sean Yan here? Okay, what about Thomas Agre? All right, what about John Engel? Brett Hinkle? These are all the people that weren't there the first time I called on them. Aaron Hoskinson? Sarah Hutter? What about Jacob Iseman? Okay, what about Kevin Kim? All right. How about Seth Aldridge? Okay, Seth, so how can we write the L2 term with a norm? Exactly. I'll put a little 2 there. Okay, and then for the other cost function, first term is the same. The second term now, when we write, we can write it also as a norm, but now we have to put a little 1 there to tell us that this is the 1 norm. And so that's the concise way to write these. So we have the two norm or Euclidean norm, and we have the 1 norm or the taxi cab norm. And the taxi cab idea comes from if you have a vector of 2 dimensions, you can think about it as a location in an XY plane, just location on the Earth. And if you are in New York City and you're a taxi driver, or let's say if you're in New York City and you're a bird and you want to go from one spot in the city to another spot in the city, you can just fly directly there, however you like. But if you're a taxi driver, you have to drive along the streets. And so you can't go diagonal through the blocks. So in that case, the distance you have to travel is actually this distance. So you have to measure how many blocks do I have to go in one coordinate axis, and then how many do I have to go in the other coordinate axis, and that is the total distance, not as the crow flies, which would be this or square root of this. So that's some intuition about what this L norm is telling you. It is a distance or a length. It's just a different kind of distance than the Euclidean one. Okay, so all right, any questions on this? So now we have our 2 different versions of the cost that we're going to be minimizing. And let's just take a peek at the first one, see what happens when we do this. So just from the last slide, this J ridge is y minus x beta Euclidean norm squared plus alpha times beta Euclidean norm squared. It turns out that because everything is nice and quadratic here, you can do the derivation of the optimal beta, the beta that minimize this. You can do this all on paper, and it might even show up on a homework problem. And it looks like this. The derivation is almost identical to the one we did back in Unit 2. The new thing is that inside this inverse, you have this plus alpha times identity matrix. So when alpha is 0, that means this goes away, right? This all goes away, and you have the least square solution. When alpha is non-zero, you have some term here, and you end up getting this little alpha identity matrix inside there, which has a certain effect. Okay, and here's an experiment which shows you a bit of intuition as what happens as you change alpha. So if we start out with alpha equals 0, we're just doing least squares. And least squares, so this is on a log scale. So if you go infinitely left on this log scale, you get to 0. But even for small values of this alpha, things are not really changing much. So on the left side here, this is approximately equal to least squares. Now, as you start to increase alpha, what happens is you're bringing in this penalty for these non-zero betas. If you go crazy and you have a huge alpha, essentially you're saying, just make this reasonable. Don't worry about this. This is not really causing much trouble because alpha is so large. This is, causing that to be big. So just make the beta 0. That's what's happening over here. All these betas are just being shut down. Okay, so this is obviously not useful for prediction. The useful part is somewhere in the middle. Probably not here either. So we can figure out, using cross-validation, where in the middle we should be. So you can make like a grid of different alphas, and for all the points along that alpha grid, you can do cross-validation, and you can find that the one that minimizes RSS in this example was right here. And so what you see is, compared to the least square solution, most of the coefficients are just a little bit closer to the origin. They're a little bit shrunk towards the origin. Now, it's not uniformly the case. Like, there's some interesting stuff where this coefficient, the brown one, started out negative, but at some point it actually changed sign, and here it was being used in a positive way. So there's more interesting stuff going on than just shrinking towards the origin, but you do see a lot of shrinking towards the origin. Okay, so, but if you step back and say, I thought we wanted to do feature selection where some subset of betas are set exactly to 0, and then the other betas are allowed to be non-zero. That is not happening here. The only time you get 0-valued betas, there's a few, specific instances where this one passes through 0, this one passes through 0, but the only place you get a bunch of them 0 together is this sort of trivial situation where alpha is extremely large. So this model is not useful for feature selection, if that's our goal. It's not setting some subset of betas to 0. It actually has an important purpose, but I think we can wait until the next lecture for that. And we'll look at lasso too, and we'll actually see that lasso does this thing we want, where it sets a subset to 0. Okay, but that's enough for today. We'll see you guys on Wednesday.